Hello, this is Dr. Gardner. Today we're going to be looking at volumes of gases related to moles of gases. That will include looking at the combining volumes of gases and chemical reactions related to their stoichiometry. We're also going to be looking at Avogadro's law, which relates to numbers of moles of gases versus its volume. Then we'll be looking at the ideal gas law equation, which will combine all of our gas law equations for the entire chapter. And then we will also go ahead and look at how gas densities relate to the molar masses of gases. So first of all, just quickly, I want you to realize when we're treating gases as ideal gases, the identity of the gas particles won't be considered relevant because we're ignoring, when we treat a gas as an ideal gas, any attractions between the individual particles, and we're ignoring the volume that they might be taking up due to the actual particle sizes. And so if we're treating them as ideal gases, an interesting side effect of these assumptions is that if I look at, let's say, hydrogen gas reacting with oxygen gas to form water vapor in that combustion process, well, if I'm starting with 2 moles of hydrogen gas, or 2 volumes, whatever those volumes might be in liters, and I'm combining that with 1 volume equivalent, or maybe 1 mole of oxygen gas, we'll notice that the 2 moles of hydrogen gas have the exact same volume per mole as oxygen gas, but since the stoichiometry is 2 to 1, we only require 1/2 the volume of oxygen gas at the same temperature and pressure conditions that we would have with respect to the 2 volumes of the hydrogen gas. So there's a nice stoichiometric relationship for gases between volumes. Now this won't be true when you're dealing with other reagents and other reactions, but with gases it's a very convenient relationship. Now if I form 2 moles of gas as my product, I'd end up with having the 2 volume equivalents that I had of the original hydrogen gas. So there's a nice volume relationship. So if I look at my stoichiometry here, a 2 to 1 to 2 stoichiometric ratio will also relate to volume ratios. A 2 volume plus 1 volume ratio will provide 2 volumes of product in this case. So you can relate the coefficients in the balanced equation to the number of volumes of gases. And here later on in this discussion, we'll be looking at the actual volume for a mole of gas in liters. So keep your eye open for that. If you were to take that volume for a mole of gas times 2, that would give you the volume of the hydrogen gas under standard temperature and pressure conditions here. If you take that value times 1, that's their volume of the oxygen gas under standard temperature and pressure conditions. And if you looked at your products, once you had formed products, assuming we had no excess reagents, we would end up with having 2 times that molar volume for the product, okay, under those standard temperature and pressure conditions. So that'll be very useful for doing some calculations quickly if you remember that relationship. Otherwise, you might have to do some longer calculational steps. Now, let's look at Avogadro's hypothesis. Avogadro's hypothesis states that the volume of a gas is directly proportional to the number of moles of that gas. So if we were to plot the volume of gases versus the moles of the gas that we had, which we'll use the lowercase n to represent moles of gases from this point forward, we'd find there's a nice linear relationship as long as we're holding all other variables constant. We're keeping it under constant temperatures and pressures. Now I can write a relationship here. If I consider that I have my volume and my number of moles, I could go ahead and say, well, my volume divided by the number of moles I have could be equivalent to a constant. Let's say it's a constant K. Now a nice product of this is that if I have my volume initial and my moles initial equal to this constant, well, the ratio of my volume under a second set of conditions and my number of moles in our second set of conditions, as long as the temperature and pressure is being held constant, which is why I'm excluding it from this equation, we can write that as an equivalent relationship. So I can say volume 1 over moles 1 is equal to volume 2 over moles 2. So that would allow me to predict an unknown volume and an unknown number of moles. Okay, so just remember that as the moles of a gas increases, the volume of that gas will increase, and this is a good prediction as long as we're holding temperature and pressure constant. If we had temperature and pressure varying, then we might want to use something like the ideal gas law equation, which we'll be looking at here in just a few minutes. Now, Avogadro's hypothesis, as we stated, will relate the volume of gases in our containers to the moles or particles of the gases. Now, this will also relate to multiple gases in a container. If I were to determine the moles of all types of gases in my container, if they're acting ideally, we don't care the identity of the gas if it's acting ideally. So we could still predict the total volume based on the total number of moles very readily. Now, if I want to look at constant temperature and pressure conditions, sometimes it's very useful to basically define a standard temperature and a standard pressure we might be dealing with. So when I talk about standard temperature and pressures, I might use the term STP for standard temperature and pressure. So if you saw a problem that said do a calculation at STP conditions, you would have to know from memory what that temperature was and what that pressure was. So standard temperature and pressure would be for the temperature 0 degrees Celsius or 273 Kelvin, and a standard pressure would be 1 atmosphere. So under these conditions, if we were to measure the mole of a gas at 0 degrees Celsius and 1 atmosphere, it would have what we call a molar volume of 22.414 liters. So I'd like you to memorize that number so that you can always determine under standard temperature and pressure the volume that you would have if we had a mole of gas. Now if I had 2 moles of gas, I'd merely multiply this value by 2 to find the molar volume for the 2 moles of gas in that case. So now if I had a mole of gas under any other temperature or pressure conditions, we'd have to use what we call the ideal gas law equation in order to solve for it. So we'll be looking at that shortly. But it's very useful to have this relationship memorized. So I'm expecting that you know the standard temperature and pressure conditions and how large of a volume of a gas would occupy 22.414 liters. If you're trying to visualize this, visualize a volume, a spherical volume that's bigger, a little bigger than a basketball, okay, with respect to size. That might help you kind of get a visual in your head for a mole of gas under temperatures of 0 degrees Celsius and a pressure of 1 atmosphere. Okay. Now let's consider that we have a balloon that was initially at 0.35 moles of gas for the moles of gas in its volume. Now since that's about a third of a mole, we know that's going to be about a third of the volume you were discussing if it were at standard temperature and pressure. Okay, now I'm telling you that the 0.35 moles of gas is occupying 8.2 liters of volume. Now let's predict if we're holding temperature and pressure conditions constant, what would be the volume the balloon would occupy, assuming it doesn't burst, if we were to increase the number of moles in the balloon of gas to 1.2 moles of gas present. We're also ignoring any pressure changes. Like I said, we're keeping pressure constant, so we're ignoring any pressure changes as we try to expand the balloon. So we're kind of thinking about an imaginary balloon that can expand without increasing the pressure inside. Okay, so if we were to look at this situation, well, we can define our variables. Our initial moles are 0.35 moles. Our initial volume is 8.2 liters. Our final number of moles is 1.2 moles. And our final volume is what we're trying to solve for, our V2. So I'm using Avogadro's hypothesis, and we're looking at changing conditions. So I have volume 1 over moles of gas 1 is equal to volume 2 over moles of gas 2. We're assuming temperature and pressure is being held constant in this case. So what I want to do then is solve for V2, so I multiply both sides by the number of moles N2, and so I generate the following equation. The volume final is equal to the volume initial times the moles final over the moles initial. Be very careful not to invert the mole quantities here, which is why I think it's very useful to label in your information given a nice table with respect to the mole quantity. So make sure you're putting 1.2 moles on top and 0.35 moles on bottom and that you haven't reversed that. Okay, now if I calculate this, I say initially I had 8.2 liters. Finally, in the end balloon, we're going to have 1.2 moles, and in the initial balloon, we had 0.35 moles. So we just predicted once we have 1.2 moles in this balloon under the temperature and pressure conditions we would have to be at, we'd have 28 liters of volume for this gas. And the identity of the gas is unneeded at this point because we're assuming it's acting ideally. Okay, now let's summarize all of the different gas laws we've looked at so far in the course. So in our last video we looked at Boyle's law. Now Boyle's law tells us that volume is directly proportional it's inversely proportional. Volume is inversely proportional to pressure, so 1 over pressure. And that's if we have constant temperature and constant numbers of moles of gas. Now, Charles' law told us that volume was directly proportional to temperature, assuming pressure and moles of gas are being held constant. We just saw Avogadro's hypothesis where we stated that volume was directly proportional to the number of moles if we had a constant temperature and pressure situation. Okay, now if we have all of these different laws that we've been looking at, let's try combining them into one proportionality relationship. So I'm going to say that volume is directly proportional to number of moles. That's what we said with Avogadro's hypothesis. I'm also going to include that volume is directly proportional to temperature, which is what we said from Charles' law. And I'm going to say that volume is inversely proportional to pressure, which is what we said from Boyle's law. So if I look at that relationship, well, we can go ahead and define that so that I can put an equal sign in here by putting a constant. So I'm going to go ahead and isolate all of my variables on one side of the equation, relate that to a constant, so I can say that we have pressure times volume over my number of moles in and over my temperature in Kelvin is equal to a constant. Now if we had an initial pressure, an initial volume, an initial number of moles, an initial temperature, we could go ahead and say that when that's equal to a constant here, well, if I were to change all of those conditions, pressure, volume, moles, and temperature, to give me a second set of conditions that would still be equal to that constant. So I can say that pressure 2 times my volume 2 will be equal to my number of moles of gas 2 times my temperature 2 in the same ratio. Now this is useful. We've just defined a new equation. It looks a little bit like the combined gas law, except unlike the combined gas law, the numbers of moles have been included using Avogadro's hypothesis. So now this is actually probably the best type of situation that we can have for writing an equation for these relationships. I can really develop any of the relationships I've looked at before. So let's consider if I had, I wanted to look at Boyle's law where we were holding temperature and number of moles constant. If I was holding temperature constant and number of moles constant, then we would see that the bottom of this equation would cancel out, and we'd end up with my pressure 1 times my volume 1 is equal to my pressure 2 times my volume 2. So if I know this one relationship at the bottom of the page, I can generate all of the other equations that we've been using previously. Let's consider Charles' law. Now Charles' law is going to mean we're keeping pressure and moles constant. So I could cancel out moles, and I could go ahead and cancel out my pressures on both sides. Okay, so my pressure and moles would cancel out. I ended up with Charles' law under changing conditions would relate to my volume 1 over my temperature 1 is equal to my volume 2 over my temperature 2. So this overall relationship with respect to all of the variables can generate any of the other relationships we were looking at. Now if I'm looking at Avogadro's hypothesis, we assumed temperature and pressure was constant. So if I kept temperature constant and I kept my pressure constant, I could go ahead and cancel those out because they would be equal to one another on both sides of the equation. We can go ahead then and see that my volume 1 over my number of moles 1 initially is equal to my final volume over my final number of moles. So we just generated from this one equation at the bottom of the page all of the other changing set of condition relationships when we had Boyle's law, Charles' law, or Avogadro's law. So usually I would just go ahead and recommend that you memorize this equality relationship to generate all of the others whenever you might need them. Now that we've generated that equation, let's go ahead and think about what we have. If we had a constant equal to these relationships, so I could say that the constant, which I'm going to write as an R, we're going to call this the gas law constant R, is going to be equal to my pressure times my volume over my moles of gas and over my temperature. I can rearrange to make a nice linear equation here by multiplying both sides by my moles and by my temperature. Okay, so if I multiply both sides by moles and by my temperature, I'll end up seeing that I end up in an equation that's pressure times volume is equal to my number of moles times my gas law constant and times my temperature here. That is my ideal gas law equation. Now with that equation, we can go ahead and find the ideal gas law constant. So let's plug in a set of conditions. Let's assume that we're at standard temperature and pressure. So standard pressure was 1 atmosphere. Standard temperature, which I've asked you to memorize, was 0 degrees Celsius, so I converted that to Kelvin to 273.15. Okay, and we knew that if we had 1 mole of gas, I'm defining that I have 1 mole of gas. 1 mole of gas has a molar volume under standard temperature and pressure, which I've asked you to memorize, is 22.414 liters. So if I take 1 atmosphere times 22.414 liters for that 1 mole of gas, I'm dividing by 1 mole of gas and dividing by my temperature. I'm just plugging these all into my relationship to get my constant. We end up with a gas law constant, which you should memorize as being 0.08206 liters times atmospheres over moles times Kelvin. Okay, so that's my gas law constant that I want to use in this case. And that's quite nice. So now we can use our ideal gas law equation, and we have a gas law constant defined. Okay. Now this is quite nice. The ideal gas law equation really will help us get a handle on all of the other relationships we've been looking at. We can calculate pressures, volumes, moles, or temperatures. Whenever I know 3 out of the 4 variables, I can go ahead and solve for the one unknown variable in this situation. Now, if the identity of the gas is known, we might be able to use molar mass to convert between moles and grams in this case by relating to the number of moles in the ideal gas law equation. So I'll show you an example of that in a moment. Okay, so let's say we have a mass of oxygen gas that will occupy a 6.0 liter container at a pressure of 700 torr and at a temperature of 25 degrees Celsius. Okay, so to use the ideal gas law equation, we need to think about the ideal gas law constant. My ideal gas law constant, which I've asked you to memorize, was 0.08206. Now that's liters times atmospheres over moles and over kelvins. Now I want to convert all of my units to match the ideal gas law equation, or my ideal gas law constant units. So I need to make sure all my volumes are converted to liters. Luckily in this case we already had it in liters, but we won't always necessarily. In case I was given a volume in milliliters, I might have to do a conversion to liters. Now my pressure in atmospheres, since the pressure was given in torr, we're going to have to convert from torr to atmospheres. And I was given a mole quantity here. We didn't start with moles, we had a mass, so we're going to have to deal with that in a moment. We had a temperature in Celsius, so to convert from Celsius to Kelvin, we had 273. I'm converting to Kelvin because I need those units to match my gas law constant. So I'd like to challenge you to always put your units for the gas law constant, remind you which of the other units in your calculations need to be converted to cancel out the units in the calculation itself. Okay. So when I'm looking at this, I use the ideal gas law equation. Remember my ideal gas law equation was PV equals nRT. You should memorize this equation because we'll be using it very frequently in this chapter. Now if I solve for n for my number of moles, I can divide both sides by the gas law constant, divide both sides by the temperature in Kelvin. We end up with pressure times volume over my ideal gas law constant over my temperature will give me my number of moles of the gas that I might have. Okay, so I had 6.0 liters, which was given. However, I had to convert 700 torr to atmospheres. Now, to convert from torr to atmospheres, remember there's 760 torr for every 1 atmosphere. So I divided by 760 torr for that 1 atmosphere. I ended up with 0.921 atmospheres. It makes sense it's smaller than 1 since I had a value less than 760. Then I'm dividing by my gas law constant, dividing by 0.08206, and I'm dividing by my temperature in Kelvin of 298.15 Kelvin. So I end up with a number of moles that's equal to 0.226 moles. Now since I have the mole quantity of the gas, if I was told the molar mass of the gas, so let's say we're told that the molar mass of the gas is 32 grams per mole, we could find out what grams of gas we'd have. Now I know the molar mass of the gas because we have oxygen gas, and in nature you should know that oxygen gas is one of the elements that occurs as a diatomic element, so it's O2. So I calculated the molar mass of oxygen gas, which I should know from memory as one of my diatomic elements is O2, was equal to 32 grams per mole. 16 grams for every oxygen. I have 2 oxygens in the formula, so that's where I'm getting the 32. So I take the 0.226 moles times 32.00 grams per mole. It tells me that in this gas sample that we are studying, we have 7.2 grams of oxygen gas. This would be an excellent type of question for the exam because you could go ahead and test a student on whether or not they could convert from their pressures to the atmospheres, so torr to atmospheres here, they're from their temperature to Kelvin, and that they recognize their diatomic gases, and that they know their ideal gas law equation. So this would be an excellent difficulty level question for medium difficulty in my opinion. Okay. Let's go ahead and look at this example. Let's say we have oxygen gas in a cylinder that we're using as a portable breathing supply for medical use. And the volume of the cylinder is 2.025 liters. Now, when the cylinder was empty at 29.2 degrees Celsius, it has a partial pressure of 723 torr. Now, just realize if we're defining the cylinder as empty, that's not always the case, because sometimes we're relating the pressure inside the cylinder versus the surrounding atmospheric pressure. And when we don't have a pressure differential, we often can't provide flow of the gas from the cylinder itself. So an empty cylinder usually has some gas quantity in it, but the pressure has dropped until we're defining it as no longer being able to deliver the gas that's within. Okay. So we want to calculate how many moles of oxygen gas remained in the cylinder when it's empty, when we know it does still have some gas quantity left in it. Okay, so we're going to use the ideal gas law equation. So remember, we're using PV equals nRT. Very important equation to memorize. I should have the gas law constant memorized as 0.08206 liters times atmospheres over moles times Kelvin. Now my temperature was given as 29.2 degrees Celsius. I want to convert that to Kelvin, so I added 273.15 to get 302.4 Kelvin. And then we had a volume of 2.025 liters. I left this in liters because my gas law constant is in liters. I converted my temperature to Kelvin, my gas law constant is in Kelvin, and we've been used to working with Kelvin with gases anyway. Okay. Now my pressure's in torr, so I said it was 723 torr, and we have 760 torr for every 1 atmosphere. So I want to divide by that 760. I get my pressure here of the gas in the cylinder being 0.951 atmospheres. I'd like to solve for the moles of the gas that's present in this case. So in order to do that, I use the ideal gas law equation, PV equals nRT. I'm going to solve for N. So to do that, I divide both sides by the gas law constant and by the temperature. So I end up with my moles of gas being equal to pressure times volume over the gas law constant over the temperature. I should always write my units down to make sure my units will cancel with the gas law constant itself. Liters, atmospheres, moles, and Kelvin. So I took 0.951 atmospheres, which we calculated above here. I multiply that by the number of moles of 2.025 moles that we're holding in the oxygen gas cylinder. We divide by the gas law constant as 0.08206 liters times atmospheres over moles times Kelvin. And I'm dividing by my temperature in Kelvin of 302.4 Kelvin, which we calculated above. Okay, so I'll notice that my liters will cancel, my atmospheres will cancel, my kelvins will cancel. I end up with final units left over of moles. And so we calculated that we still have 0.0776 moles of diatomic oxygen gas present when we are no longer delivering gas from the cylinder because its pressure has dropped too much. So that supposedly empty cylinder actually still has some gas content within it. It just isn't delivering it effectively because its pressure is going to be small enough that it's not greater than the surrounding atmospheric pressure. Okay. Now let's try a similar example. Let's say our temperature was 18.1 Celsius, 755 torr, okay, and that the tank volume was 1.85 liters. Let's go ahead and try to calculate the mass of oxygen gas now that would remain in the cylinder. Okay, so we're going to take an extra step this time. We're going to go ahead and go from moles to the mass. So I need to know it's a diatomic gas in order to do that calculation. Okay, so I go ahead and define my variables. So I have my gas law constant that I should memorize, 0.08206 liters times atmospheres over moles times Kelvin. I should know the molar mass of oxygen gas is 32 grams per mole because it's a diatomic elemental gas. Remember that you should know your 7 diatomic gases on the periodic table. That would be hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Kind of makes a 7 from nitrogen down to iodine, and that reminds you of the 7th gas, which is the hydrogen. So those are all diatomic elements. In fact, I misspoke. They're not all gases, but they're all diatomic elements. Many of them are gases, but not all of them at room temperature and atmospheric pressure. We also have a temperature that was 18.1 Celsius. We convert that to Kelvin by adding 273.15. We end up with 291.3 Kelvin under that temperature. And we end up with a volume for the cylinder that was defined as 1.85 liters. Now, my pressure was 755 torr. We need to convert from torr to atmospheres to match the units on the gas law constant. So I divide by 760 torr for every 1 atmosphere. We're going to end up with 0.993 atmospheres for our pressure. We would like to solve for the mass of the gas. In order to solve for the mass of the gas, I'm going to first of all have to solve for the moles of the gas, and then we'll use the molar mass to determine the actual mass. Okay, so all I've done is bring all of the defined variables over to the next slide. We're using ideal gas law equation. I should recognize that's pressure times volume equals to number of moles times my gas law constant times temperature. You kind of remember, if you try to pronounce this, it looks like piv nert, right? That might help you remember the actual formula. Now I'm going to solve for n, which is the only variable we don't have, and from the number of moles from n we can get the mass, which is a lowercase m here. Okay, so my number of moles will be equal to my pressure in atmospheres times my volume in liters over my gas law constant over my temperature in Kelvin. So I have 0.993 atmospheres that we calculated here above, times 1.85 liters, which was defined in the original question. And I'm dividing by the gas law constant, which I should have memorized. And I'm dividing by my temperature in Kelvin, which we defined above as well. So I have 0.993 atmospheres times 1.85 liters divided by 0.08206 for the gas law constant with units of liters times atmospheres over moles times Kelvin. And I'm dividing by 291.3 Kelvin. Okay, I'll notice that my kelvins cancel, my atmospheres cancel, and my liters cancel. I'll end up with an answer in moles, and so I calculated I still have 0.0769 moles of diatomic oxygen gas present in the cylinder under this set of conditions. Now I'm not quite done with the question because I want to convert to grams. So to convert from moles of the gas to the mass of the gas, I need the molar mass. So the molar mass of the gas, I'm using capital MM here to indicate molar mass, is 32.0 grams per mole of oxygen gas, because each oxygen mole of monatomic oxygen would be 16, but they come in packets of 2, so I have 16 times 2 is 32, right? And then if I go ahead and take the number of moles from the previous calculation, which was 0.069 moles, now that I have the moles of the gas and I have the molar mass of the gas, I can easily convert from moles to grams by using the molar mass as a conversion factor. So realize my moles of the gas is just equal to the mass of the gas divided by its molar mass. Okay, so I rearranged to solve for the mass of the gas. So mass is equal to moles times molar mass. We've did this quite a bit whenever we're doing calculations converting from moles to grams previously in the course. So I can go ahead and take the number of moles of 0.0769 moles times the molar mass of the gas. For the diatomic oxygen gas is 32.0 grams per 1 mole. That would be equal to 2.46 grams. Now the reason I'm using a diatomic gas here is I frequently see students forgetting to consider the true molar mass of the oxygen gas, or any diatomic gas. They'll sometimes just look at the periodic table and use the value off the periodic table even though it's diatomic, and they'll get an incorrect answer. That would only in this case give you half the number of grams you actually have, because we have to use the actual mass of the gas particles. In this case it's diatomic, so I had to use 2 times the mass from the periodic table. Be very careful, it's a common mistake that I tend to see. Okay, so for the last part of the discussion today, I'd like us to look at gas densities. When I'm looking at gas densities, I should realize that a heavy gas with a higher molar mass will have a higher density than a lighter gas with a lower molar mass, assuming that the temperature and pressure for the two gases are identical. Okay, so here's an example of a balloon that contains helium, and here's a balloon that contains argon gas. The argon gas is higher density, is more dense than the surrounding air. The helium gas is low density, it has a smaller density than the surrounding air. If I were to look at the densities of a variety of gases, we can see that as the molar mass of gases increase, the density of the gas also increases. We can also see that the molar masses for gases are increasing as we go down the periodic table, and so our densities increase as we go down the periodic table. If we start to look at the molar mass of diatomic gases, we have to consider that they are 2 times the mass on the periodic table. Or if we have more complex molecular gases like carbon dioxide, it has a molar mass of 44.01, which is going to be more dense than air, because air's major component, about 78% of it, is 28.02 grams per mole for diatomic nitrogen gas. So CO2 gas is heavier than air and will tend to sink if we were to release it from a reaction. It tends to be below the surrounding atmosphere until it has a chance to mix uniformly. So as we have increasing molar masses, though, we're still seeing densities increase. So for example, if I had sulfur hexafluoride, it has a molar mass of 146.1 grams per mole, and its density would be 6.51 grams. Now, radon gas has a molar mass of 222. It has a higher molar mass, and so as you might expect, it has a higher density. We're going to look at how to calculate these densities in a minute. The radon gas would have a density of 9.90 grams per liter. Notice that we're working with the densities of gases in grams per liter here, not grams per milliliter and not grams per centimeter cubed. If I want to compare gas densities to solids or liquids, I would have to convert the volume of liters to milliliters or centimeters cubed. Remember, 1 milliliter is equal to 1 centimeter cubed, so that would be the same value for those two relationships. So be cautious there. Now let's see how we can calculate the density of gases from their molar masses. Now a heavy gas will have a higher density than a lighter gas at the same temperature and pressure conditions. We've just shown that with some data on our previous table. Now I can go ahead and calculate gas densities by using the ideal gas law equation, but we're going to have to manipulate it slightly. So we're going to take our pressure times our volume is equal to our number of moles times our gas law constant and times our temperature. I'm going to go ahead and rearrange this, and I'd like to look at, in order to find densities, now normally densities is grams in mass over a volume in centimeters cubed or milliliters or liters for gases in this case. So if I want to get the mass of a gas in grams per liter, well, maybe I need to get a relationship that starts to look at that. Now, since I don't actually have a mass in the ideal gas law equation, I'm going to go ahead and use moles. So I went ahead and isolated the moles here by dividing both sides by my gas law constant, my temperature, and I divided both sides by my volume. So I end up with moles over my volume is equal to my pressure over my gas law constant over my temperature. Now I'm not quite there because this isn't mass yet. This is moles at this point. So I need to recognize that molar mass. Now I'm going to use a capital M for molar mass here. Now be very careful. I am not referring to molarity, which is a concentration term, which would be moles of solute per liter of solution. So in this case, in this discussion, that capital N actually stands for molar mass. If you want to prevent confusion, maybe you can put MM there for molar mass if that helps prevent any confusion for you. Now, if I recognize that my molar mass will be equal to my mass in grams over my moles of the substance, well, I'm going to use a lowercase m for mass in grams. I'm going to use a lowercase n for moles. I'm going to go ahead and solve for n. And so when I solve for n, I went ahead and multiplied both sides by the number of moles and divided both sides, in this case, by my molar mass. So I end up with the number of moles is equal to my mass divided by my molar mass. Let's think about the units. My mass is in grams. My molar mass is in grams per mole. So my moles will cancel. I'll end up with units of moles. Okay, so once I have my units of moles here, you can see it relates to the n value. Okay, so I'm going to substitute that in. So I'm going to substitute my mass over molar mass into my equation for n. So now I end up with my mass over my molar mass divided by my volume here is equal to pressure times my gas law constant and divided by my temperature. So remember, capital M is molar mass, not molarity here. So I went ahead and I multiplied both sides by my molar mass. If I do so, I end up with mass over volume. That's my density. So my density is equal to the mass over volume, which will be equal to the pressure of the gas times the molar mass of the gas over my gas law constant over my temperature. Now you should either memorize this equation or be able to derive it the way I showed you here on this slide. Okay, so what's nice to see here is if I want to look at density, well, density is directly proportional to molar mass, which is what we were seeing with our previous data on our table. Okay, they're directly proportional. So let's go ahead and practice this. Let's find out what the density of methane gas, CH4, at standard temperature and pressure would be. Okay, so I know my density is equal to my pressure times my molar mass over my gas law constant over my temperature. So if I want to find my density, I need to calculate the molar mass of the gas I'm dealing with. Since I defined it as methane, it has a formula of CH4, 1 carbon atom and 4 hydrogen atoms in the molecule of the gas. So my pressure in this case was only defined by telling you STP. So I must know that standard temperature is 0 Celsius. Standard pressure is 1 atmosphere. So my pressure is 1 atmosphere. My molar mass for methane is 12 for carbon plus 1 for each hydrogen. So that, and it's 1.01 for each hydrogen. So I end up with 16.05. 12.01 for carbon, 1.01 for each of the hydrogens times 4. That's my grams per mole. Now I divide by my gas law constant of 0.0821 liters times atmospheres over Kelvin and over moles. And I'm dividing by my temperature in Kelvin, 273 Kelvin. So what we'll see here is that my atmospheres cancel out, my moles cancel out, okay, my Kelvins cancel out, and I'm going to get grams per liter for my unit. So that's a good density set of units for gases. So we find the density of methane gas is 0.716 grams per liter. Okay, so that's a very good way to calculate this. Now what I'd recommend that you do in groups in your class next is that you try to calculate the density of a noble gas, which has a density value. Actually try to calculate the identity of the noble gas. I gave you the density, so now here we're going to have to solve for molar mass. So I gave you the density of 2.71 grams per liter, okay, at 3 atmospheres and 0 Celsius. I'd like you to identify that gas, so please pause the video here and go ahead and work on this in groups and see if you can find the correct gas identity. Okay, so once you've had a chance to calculate this for yourself, hopefully you identified the gas as neon, as B here. Now let's see how we would calculate that. Now we know our density of our gas is going to be equal to my pressure of the gas in atmospheres times my molar mass. I'm just using capital M for molar mass here in grams per mole over my gas law constant R and over my temperature. Now I'm going to rearrange my equation to solve for the molar mass because I want to know the identity of the gas. So my molar mass will be equal to my density, because it was equal to density here. I'm going to divide my density by pressure and multiply my density by my gas law constant and my temperature. So it's my density times my gas law constant and times my temperature in Kelvin divided by my pressure in atmospheres. So now I see that my answer in here for my molar mass could be calculated by taking the density value that was given as 2.71 grams per liter times my gas law constant of 0.0821 liters times atmospheres over kelvins times moles. And I multiply my temperature. Temperature was defined as 0 degrees Celsius, but we need to convert to Kelvin. So I'm going to multiply by, in this case, 273 Kelvin. Sorry, that's a 7 there. I'm dividing by my pressure in atmospheres. We said that the pressure was 3 atmospheres. So I have 3.00 atmospheres. So when you see our atmospheres would cancel, our liters would cancel, our kelvins cancel. We're going to get grams per mole for our final answer, so that's our molar mass. And so you should have calculated that the molar mass here for this noble gas was going to be about 20.2 grams per mole. Now the best gas to match that was the neon. Okay, so hopefully you did that correctly. If not, you should practice some of these density calculations. Make sure you're also doing your homework related to them. So next time we'll talk about partial pressures as well as some other gas calculations. Thank you very much, everybody.